All right, let's get going. So we are here Monday, March 31st. Hope you guys enjoyed March. It's over today. Let's see. Here's what we're going to do. We're going to talk about Unix tip of the day, this program called sed. I'm going to give you like a very brief, here's kind of what sed can do, and then you can go check out all the other different fun things it can do. It stands for Stream Editor, for what it's worth, and we'll go over what that is. Then we will go over the midterm answers. I promised you I'd go over the midterm. What I'll do is I will actually post the answers online. Somebody already emailed me, and I completely ignored the email. So I will put that online, hopefully by the end of today, if you want to take a deeper look into it. Then we will go into sorting, and we're going to cover 3 different sorts today. We're going to talk about this thing called the merge sort, which is just like it sounds. You're taking different lists and merging them together. And then we're going to talk about quicksort, which is one that's probably used more often than any other sort for fast sorting. And then we're going to talk about a completely different type of sort, which is not a comparison sort, called radix sort, which is a completely different way of thinking about how to sort integers and other sorts of things. OK, questions before I begin? All right. Before I do anything, let's go over the sed. I think I got it in backward. There we go. So as I said, sed, it's a Unix program. It stands for Stream Editor, which means that you send a data input stream into it, and then it processes it in some way and then sends an output stream out. OK? Here's what you can do. One thing that is sometimes important or sometimes necessary to do is, let's say you have a file and you need to do like some sort of global search and replace in that file. Right? So you want to change all instances of green to blue. Well, you can do that using sed in the following way. You could say sed s, which stands for substitute, and then the slash is actually a delimiter, and you can make it whatever you want. But whatever let's say you do slash and then something, and then the slash again says that's the first word, and then the next word, and then another slash, and the G says globally replace it, whatever you're trying to do. Meaning on a line, don't just replace the first instance of blue. If there's other instances of blue in there, replace that, or sorry, green, replace that one as well. OK? Let me show you. All right. So I think I have, there we go. Before I did ham and turkey. This time I'll do blue and green like I did before. Blue, green. And what I'm doing here is I'm actually using colon as the separator instead of slash. It doesn't actually matter. OK, and I have the text of green eggs and ham, Dr. Seuss, in here. And what I'm going to do is I'm going to replace everything where it says blue with green. It would be the other way around, wouldn't it? Green and then blue. It should be green and then blue. All right, let's see if that works. OK, and all I'm doing is pipe. This is saying pipe in green eggs and ham. Just like on our homeworks, we can pipe in part of the input. All right, and here we go. Let's see. I do so like blue eggs and ham. Thank you, Sam. I am. So you can see that it does that. If you wanted to, you could pipe it. You could have it go out to like blue eggs and ham, right? And then it would just send it to there. And now blue eggs and ham is the actual file. So this is like one of the things that sed will do for you. Now, sed is actually really powerful in that what you're trying to search for here is based on this thing called a regular expression. And regular expressions are like really powerful ways of telling a program what you're trying to search for. OK, like what the actual parameters are, and like wildcards and various ways of writing things. It's a whole other topic in itself, like a huge topic in itself. But it's relatively easy to go and find information about. So anyway, so that's sed. It will do substitutions and other text modifications. For instance, there's a sed line to put line numbers at the beginning of every line in your whatever code. If you wanted to have a text file and you wanted line numbers, you could do that. Or if you wanted to double space it, if it was only single spaced, all that kind of stuff. OK? Questions on that? Unix tip of the day? All right. All right, so let's see. There's a website here you can go to. It's on the web. It's on the web here in the presentation that says where to go to get lots more information about that. Okay. All right. OK. Let's go into the mid-year. Let me show you the midterm exam. Nope, there it is. OK. All right, we already kind of went over most of the details about the mid-year. And it was, for the most part, you guys did very well on it. I have some specific comments about how to, nope. It's just going to keep going. The little thing doesn't want to turn off. Hold on. There. Nope. OK, stop. All right, enough. Whew. All right. So anyway, so the mid-year is very good. Let's go through the questions. I'll fly through these. We're not going to spend much time on them. But if you have specific questions, you can either ask them now or certainly look them over on your own as well. OK, so question 1 said it was about arrays and writing code. I hope this wasn't a surprise to you. I kind of expected you guys to know how to do this, right? To expand a list. Not rocket science here. Many people forgot the following. Many people forgot day capacity equals day capacity times 2. They forgot to actually set that variable at the end saying, hey, now I'm this big. Right? You do it up here for the array, but then later you're going to need to use that again. OK. Explain why inserting an element at the end of a sorted array is order 1 and why inserting at the beginning is order n. I think most of you guys got this. If you're doing it at the end, you don't have to move anybody. If you're doing it at the beginning, you have to move everybody. So that's the difference. All right. And then I got some concern that we hadn't gone over caches enough to answer this next question. And that's a fair enough comment. Although really what I was looking for is what do you know about arrays, right? The point of a cache, right, is to take a chunk of memory in a contiguous amount of memory and put it all into this faster memory. And then whenever those elements actually get accessed, it's going to be very fast. You can do that with arrays. Why? Because they are contiguous. In other words, if you're walking your way through an array, element 0, element 1, element 2, element 3, element 4, right? Well, you're going to access them right next to each other, right? Because they're in memory that way. Well, the nice thing about the way a cache works is if you access an element, the cache will say, is that element in cache yet? It's not? Oh, I'm going to grab a whole chunk nearby, including that one, put it all in that fast memory. OK, so that's what's really going on with the cache. If you tried to use a linked list, that breaks caches. Why does it break caches? Because here's your node 1 in this chunk of memory. And it's pointing to node 2, which is over in this chunk of memory. And that's pointing to node 3, which is back in some other chunk of memory. Every time you access the next node, the cache says, oh, maybe I need to load that little bit of memory. So it chucks out the old stuff and loads in the new stuff. Now, it's not quite that simple. But the basic idea is linked lists aren't next to each other. So the cache, which has to have elements next to each other, can work efficiently. Now, again, I didn't expect you to know all of that about it. But the idea was, hey, what makes it so that arrays would be anything? Well, they're right next to each other in memory. OK, questions on that? Yes?
Just saying that arrays store their elements in a continuous rotation of memory, would that have been enough? Or do you need the part of that?
That should have been enough. If you didn't got points off, let me know. OK? That's true with any of this. If what you see up here is close enough to what you think you had, I am not obviously, I don't want you guys to grade grub, as they say. But I also don't care if we made a mistake. I want to fix that mistake. So yeah, and if you think if it's a gray area, I'm happy to discuss it. I won't always give you the points, but I'm happy to discuss it. OK? All right. So let's see. Question 2. This one was, it said, hey, where are the operator equals lines up here, right? Circled them. Now, most of you guys circled this one, and then a bunch of you guys circled this one. Well, you were absolutely right. I was wrong on this. Or the grading, I forgot that I didn't see this one, or I forgot it. And so if you circled this and somebody took off a point, I will give you that point back. OK, so I think I'm just going to go through them all. But if you want to email me and say, hey, I got a point up there, I'm happy to fix it right for you. So that's no big deal. If you circled that and got a point off, I don't want you to have a point off, because that indeed is an equals operator overload, because it's copying the day items from this day list into this day list, or it's copying it one back So that's that. We did not take off points if you missed this ampersand here, although we tried to write it in there to say what it actually was. Again, if you lost points on that, let me know. The reason was because I figured, OK, yes, you should know that you're returning a pointer. But at the same time, if you typed this in without the ampersand and tried to compile it, it would instantly like crash. Like it would say, the compiler would go, hey, what's wrong? So again, you should know that, but it's not. I didn't take points off. Yes. Very good question. What's the ampersand do? Well, if this is a day list, that's an item in a day list, an object, right? The ampersand says, what's the address of that object? That's what it says. OK, now, in this case, it says that. Up farther, I believe. No, we don't have it here. If you were to declare a variable with an ampersand, it kind of means something else. It means a reference variable, which unfortunately, I think C++ didn't do the right thing when they said it's the same thing. I mean, they're related, but they're different enough that you can get them confused. But if you're referring to a variable in code with the ampersand, it means give me the address of that. OK? And you can do that for variables or other items as well. OK? Let's see. Yes?
What
Allie.
type does this function return?
This function returns a pointer to a day. And a pointer to a day means an address of a day.
Versus if without the ampersand, it would actually return a day.
Yeah, it would return the object that is a day. Yeah. That's the difference. If there's kind of some it's hard to explain in a bit. Like I don't think it's worth getting into details like that too much right now. But if you want, I'll certainly walk through some of this stuff with you later. OK. So yeah. So this says give me a pointer to a day. So therefore, you have to return the pointer or an address, which is a pointer. A bunch of people forgot that or didn't see that. Look, if this is what we're trying to return, then you need to actually return day list day count minus 1. Okay? And I did get some more good feedback about this problem as well. In that, OK, I didn't put a what did we call it? A purpose statement, right? I didn't put a purpose statement to say exactly what this does. This was from the homework, so I kind of expected you to know it. But in the future, I will try to be a little more specific about that. And also in the future, I probably won't give you code examples that are directly from the homework. Just so I'll probably give you slightly more generic problems that I think will rely less on you having known exactly what was done on homework. So, all right, that was that. OK, you guys did for the most part, you did great on this asymptotic behavior. A few people put that the asymptotic behavior for this one was n to the fourth, n to the third, n or plus n squared plus n. Remember, any polynomials that are less important than another polynomial. In other words, n cubed is less important than n to the fourth, because n to the fourth is going to overwhelm n cubed. Then that just goes away. So all of these immediately go away, and the only thing you're left with is just the n to the fourth. Okay? All right, most of you guys did great on that. Let's see, what's wrong with the following logic? All right, so this was saying, hey, look, insert. Actually, this one wasn't the one. This is not the one I'm thinking of. Inserting the front of an array is order n. Oh no, this is the one. Expanding a dynamic array is order n. Therefore, because expansion is included inside the method to insert, why isn't it, or it should be order n squared? Well, a number of you guys said it would only be n squared if you had to call the expand every single time. And we took points off for that because what's going on is it's doing if you expanded every single time, you would do on order n like this, and then you would do another on order n to do the insert, right? Is that n squared? If you're doing n and then another n. No, what is it? 2n, yeah. A bunch of people put n squared. It's actually just 2n, right? So you had to be a little careful with that one, right? OK. All right, so the linked lists one. Again, pretty good. Most everybody actually drew the picture very well. But a number of you guys forgot or didn't think about the fact that if you're walking through your list, all right, two things actually. The first thing is if you're walking through the list, if you're canceling breakfast, you'd better check and see which node is breakfast. It might not be the first node, right? You could have like workout or something right before it, something like that, right? So you need to know that there could be another node in there you have to check. So you have to walk through the list. That was the first thing a lot of people missed. Another thing a lot of people missed was, and this one was kind of, you don't think about it until you sit down and you go, oh, I get what I did here. So you got to breakfast and you said, I need to cancel breakfast, so I'm going to take event list and I'm going to point it beyond lunch. And many of you didn't have the temporary variable in there. So you said, move event list to point to lunch and then delete breakfast. If you don't have a temporary pointer, what's pointing to this node besides event list? Nothing, right? And so if nothing's pointing there and you all of a sudden move the event list point here, you've lost the only link you have to breakfast, and therefore you can't delete it. So that's why we need a temporary one in here to point to breakfast, walk through, eventually point to the one that is the one that you're going to delete, so that you can delete, you can move the event list pointer and delete the temp. Yes, Manvi. Right. I know a lot of you assumed that. You can't assume that. Sorry. It's just an assumption you can't make in this case. I mean, if you cancel event breakfast is like a function name, right? So breakfast would be some like breakfast node that looks a lot like this one. It's not like this one. You see what I mean? All right. That should have been more clear. I'll take the hit on that. I think you're right. I'm just saying 80% of people got this right because they knew to walk through the list. But, yeah. Yeah. Yeah, I hear you. You thought, well, OK, yeah, all right, I guess. Then you wouldn't have needed to move any pointers, would you? I guess not. Yeah, that's weird. Would I have asked that? I don't think I would have asked that. But anyway, we can. If you think it's wrong, if you think I graded it wrong, come and see me. All right. OK. Same thing for the next one here. A number of people did the same thing here. Schedule event lunch. Fewer people did this, but they didn't say they just said, or fewer people said just insert lunch between breakfast and dinner. But you had to say I need to check where I need to put it, right? So I need to put breakfast. I need to put it after breakfast or after whatever link. And so you check. You create some temp to point here. You also create a previous to point there, and you need the previous because it's a singly linked list. So you need to know, the one you need to be able to get to the previous one you need to go from. OK? All right. All right, this problem. So this problem was worth 6 points, and I think the average was about 2.7 points on this problem. This was another one that I think was, it was a hard problem in that I took lines of code out that you didn't necessarily know were going to be there. And when there's an absence of code, it's harder to debug than something written there being wrong. OK? But how would you go through and figure this out? Well, what you should do if you don't know what if you don't really know what's trying to happen here, first of all, you should know how to cancel an event. In fact, you just did it on the previous page, right? You actually just drew a little how to cancel an event, right? But what you should do is you should think about this and you should say, all right, what are my cases? OK, my case is the node somewhere in the middle. My case is the node somewhere at the beginning. My case is somewhere the nodes at the end. Is this code, as it was originally written, going to take care of all those cases? Maybe, maybe not. If the list is empty, what happens? What if the node I'm trying to cancel is not included in the linked list yet? I'm trying to cancel some node that doesn't actually exist. You have to think of all those cases, right? Had you thought of the case that said, if the linked list is empty, if the event list is empty, well, the minute you do this, setting temp equal to event list, if event list is null, when you go down and try this, you will segfault. Because there is no, you cannot reference a pointer from a null. It just doesn't work. All right? So you need to be able to return. Same thing down here. This one was, I think, a little more straightforward. If you're going through here and you keep going through here, well, what if you end up at the end of your list? If you end up at the end of the list and you haven't found what you're trying to cancel, you'd better return, or a break, or something like that. OK? And then finally, the other little problem was this one down here. Once you're trying to cancel the event, just setting the previous pointer to be the next is not going to do it. You have to set what previous is the pointer previous is pointing to. That its next needs to point to the next of the one you're trying to jump over. OK? I know that was a hard one. Yeah.
If we put like a general statement at the beginning saying
Uh-huh.
add a bracket over the whole function.
That's fine too.
Oh, okay. If we got, can we come to you?
Yep, if you got points off on that, let me know. Yep, if you put a bracket here, if you said if temp equals null, not equals null, and then bracket for the whole thing, that would have been fine too. Yep, good. OK, all right, that was the ugly problem. In the future, I'll probably try to, like I said, not have one that's directly related to homework, but also maybe I wouldn't, leave out so many pieces of code. I don't know. Yeah.
So I said that one of the errors is that you didn't have to delete temp because it was not created with new. I'm guessing that's not right.
Well, you do have to delete. Yeah, so in this case, because it's a linked list, you're going to have to declare all. You're going to have to use new to create all of your nodes. Like there's really no other way to do it.
But so like event node temp gets event list, that temp pointer wasn't created with new.
Ah, right. When you say down here delete temp,
Yeah.
OK, remember what that means. Temp is whatever node. Well, first of all, it's the node that you're trying to cancel. Right? So when you're trying to cancel that node, well, you're going to be left with that node at the end, and it's not going to have anything pointing to it after it returns. So you need to delete it. So that's really what's going on there. But up here, if you say event temp equals event list, OK, remember this is just a pointer. First, it points to event list, which is a node. Then there might be some other node. Then there's some other node. Eventually, temp will point to the one you want to delete or cancel, and that one needs to get deleted. So it's
So delete temp means delete what temp is pointing
Yes.
to rather than delete the pointer.
right. There's really no, you really don't delete pointers per se. Like you can't, like deleting temp does not say delete the pointer variable temp. It says delete what temp is pointing to. It's a C++ kind of way of thinking, I guess.
What if you had created temp with new? Or is that not possible?
Well, you wouldn't really do that up here. But I mean, I guess if you had, sure, you would have had to delete temp and again. I mean, you'd have to delete whatever. So let's say up here you said something wacky like event node temp equals new node or something, right? New event, right? Well, then the minute you got down here and you set temp equal to the next, you've lost the pointer to the thing you just created. Like you needed to delete that before. So again, it's pointer arithmetic or pointer math, and like dealing with how pointers work is a tricky subject. But it has to do with delete means delete whatever I'm pointing at. Yeah, I know it is confusing. All right. OK. This problem, I actually like this problem. And you guys, for the most part, did very well on it. The remainder function, OK, I gave you a little thing and said, hey, you can do remainders by subtraction. OK, and if you have the following recursive function, I mean, it's really 2 lines long. And I kind of told you, I think I gave you a hint here. Yeah, this should be a very short function, right? If, in this case, what you're doing is, so let's go through this. If you're doing remainder 13, 5. OK, the remainder of 13 divided by 5 is 3, right? So what it should do is in a and b, OK, 13 and 5. All right. If a is less than b, return a. Well, 13 is not less than 5. Otherwise, return a minus b and b. Return remainder of a minus b and b. A minus b in this case would be 8, and remainder of 8 and 5. Well, let's see if this works. 8 and 5. 8 is still not less than b, or 5. 8 is still not less than 5. So we return 8 minus 5, which is 3, comma 5. Recurse through again, the remainder of that. Recurse through again. A is now less than b. 3 is less than 5, so we return 3. And so it actually works. And believe it or not, it works for the other case too, if you said remainder of 5, comma 13. Right? So it works in both cases. So it's kind of a neat little recursive one. You would never do this way. Right? You'd always use some sort of division, but this is the way you might do it. All right? OK. The power function, again, most of you guys did well on doing this one. A whole bunch of people put, instead of having a temporary variable here, they just said, I can use a, which is, so if I want to, here we go. I'm going to try to get this up here. Hold on. What they said was, OK, I'm going to say, instead of temp equals temp times a, I'm going to say a equals a times a, because that'll move the answer of a times a into my function here, right? OK, don't come down on me. All right. when you say something like 2 raised to the 3rd power, obviously, right, that's 2 times 2 times 2. In other words, 3 times you're multiplying by 2. OK, so let's think about going through a loop where b is decremented from 3. So if b equals 3, right, b equals 3, and what a lot of people said was a equals a times a. OK, a starts out as 2. 2 times 2, what's this a going to get the result of? The result is going to end up as 4. OK, all right, and then b equals 2, because we're going through the loop again. And you're saying a equals a times a. Well, a is now 4, and a is 4. So you're going to have 16 here instead of 8. OK, and so you end up getting too many a's. So in fact, the comment I put on a lot of yours was too many a's, right? Because you don't want to do it this way. So you do need some sort of temporary variable in here to hold a value. Now, some people did it differently. They said this was a, and they had the logic worked out. But the point is that you can't just say this, because you'll have too many. You'll end up with numbers that are way too big. This doesn't work logically. Okay. Questions on that? All right. This one, so recursive functions tend to be slower. All I really wanted you to say was that storing functions on the stack are expensive, right? And a program has to do this every time it recurses. And I guess I didn't really put this in here, but did I put it down farther? No. I kind of wanted you to mention something about storing state, right? I mean, storing function on the stack is expensive, right? Storing state is kind of the idea here. I mean, a lot of people put, oh, you have to loop through, or you have to call it many times. Well, your loop is doing looping many times. That's not really it. The whole point is you have to save it, and you have to take up more space. Recursive functions. Okay. All right. This one, most people did great on this one too. Push each character. So if you're reversing a string, take each character of the string, push it onto a stack, and then pop every value off a stack in order, and the string will be reversed. Easy enough. Okay. All right. Let's see. Circular queues. There's a lot of red words here, but the idea that I was really looking for, if you said the following, I probably gave you full points, right? You're generally in a queue, in-queuing and de-queuing at about the same rate. So I wanted you to say something about the fact that, look, the reason that you end up with extra space behind you in the queue is because, or in the array, is because you're in-queuing and de-queuing at about the same rate, and all that extra space is now unused. If you don't do a circular queue, then you certainly have to use more space, like make new, like a new array or something, and copy all these variables. But you don't need to, because you've got all that extra free space. So you might as well make it circular. I was kind of looking for something along those lines. I was relatively lenient in grading this one, but I did want you to say something about the fact that you're doing it at about the same rate. OK? Yeah, Dylan. Yeah, I mean, in general, you have to be at least to a first approximation in-queuing and de-queuing at the same rate. Otherwise, you're going to fill up your queue or have it empty. And then, I guess if it was empty, it'd be about de-queuing, really. Yeah. Other questions on that? OK. All right. This question. So in class, we talked about the following algorithm. If you're going to replace or delete a node from a binary search tree, right? You go to the right and then find the right node and right child, and you find the minimum value of that right child, which means go all the way to the left, and that's it. And this is the minimum value. You put that minimum value in place of the one you're deleting, and then delete this one, which means in this case just jump over to do a link straight to 52. Like that. Now, most of you guys put some sort of balanced tree here. OK, so I gave you some points for putting a balanced tree. But if you didn't use an algorithm that was the one we talked about in class, how did I know how you actually did it? I mean, you could have scrapped everything and then rebuilt the tree from scratch. I just don't know, right? So I took off a point if you didn't do the correct algorithm but still had a balanced tree. If you did it the other way, if you went left and went all the way right, I guess you probably have some argument to say, oh, I did it a proper way. It's exactly the same except reversed. But I wanted to do it the way we did it in class. If you want to complain about that, I'll probably sneer and then give you the point. All right. Questions on that? OK. All right. Let's go through the AVL tree one first. Whole bunch of people did the following. They said they appropriately put 10 down here, which is what we were doing. We were, where did the question go? We were inserting 10 into this AVL tree. OK. So they properly put 10 down here. And then they went straight up to 60 and said, does it balance? 1, 2, 1, 2, 3, 4. Nope, I better rotate 60. 40 goes up here, et cetera. That's not the way the algorithm works. OK, the algorithm does the following. It says, put the node in there and then walk backwards and check every node backwards to see if it is balanced in an AVL fashion. Because then you don't have to balance the whole tree if you find one that is. So it was 10. And then 20 has 0 on this side and would have 1 on this side, so it's balanced in an AVL fashion. 30, 1 and 1, 2, it's balanced. 40, 1 and 1, 2, 3. 40 is the one that needs to get the rotation. So how do you do that? You take 30, you move it up here. 40 goes below 30, and 50 and 35 fit in there. So 30 and 40 and 35 like that. Okay? I gave you some credit if you rotated 60, but it wasn't full credit because that's not the one that needed to be rotated. And by the way, notice now, once you rotate 40, you do not need to rotate 60. Only a single rotation necessary. Okay? Questions on that one? All right. OK. So the bonuses. Let's see. This one was really tricky. All right. I gave partial credit if you put 31. I gave half a point credit if you put 31. The answer is actually 30. As it turns out, and you wouldn't necessarily know this is why it was a bonus, but when you have signed integers, you've got a whole bunch of integers less than 0, a whole bunch of integers greater than 0, or I guess the other way around, and you've got 0 in there, right? Well, it turns out that there's generally, the way they do it on normal 32-bit PCs is there happens to be one more negative value than a positive value. And so actually, 2 to the 31 is actually 1 greater than the maximum positive integer. So it should be 30. So anyway, if you said 31, that's right. Or I gave you half credit. All right, this one. What I should have said on this one was that this was a string, although I'm not sure it would have mattered to most people. A C string, a character string. Turns out, character strings so both D and S were character strings. Character strings go like this. Character, 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 0. And the 0 tells you I'm at the end of the string. OK? That's how they work. Character, 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 0. And that 0 says I'm done. Take a look at what this crazy obfuscated C sort of while loop does, although it's actually a classic one-liner for doing stuff. What it's saying is, while this whole statement is true, just keep doing whatever is inside this statement, right? That's kind of what it's saying. And what it's doing is it's saying, all right, D equals whatever D is pointing to equals whatever S is pointing to. In other words, copy what S is pointing to, that character, into D. And then increment D and S, meaning go 1 over. OK? And then do it again. And then copy S to D and move over. Copy S to D and move over. Copy S to D and move over. When you get to S being equal to 0, what it does is it says this equals 0. And all C++ expressions return the value of, so if you say A equals 4, the return value of that is 4. If you say A equals 0, the return value is 0. 0 happens to be false to C++. So when you get to 0, you copy 0, return 0, this whole thing becomes 0, and you stop copying. OK? It's clever. But if you write this these days, like people will be like, what are you talking about? Why would you do that? It's like too much obfuscation in there. Right? But anyway, so all it does is copy S to D, and that's it. OK, let's see. Why did I mention, what was the problem with Amazon? Too few reviews can cause items to go to the surface if they're good reviews. I already talked about you guys thinking I was in the Army. And then this is where I was last year. African country called Djibouti. It was not Australia. Most of you guys put Australia. I was there like 15 years ago when I was in the Navy officially. I would have loved to have been in Australia last year, but I was in Djibouti. So, all right, questions on the mid-year? I will post this later today. All right, awesome. OK, back to sorting. All right, so we've talked about what kinds of sorts. We've talked about insertion sort. We've talked about selection sort. We've talked about shell sort. And all of those sorts were pretty good. At least shell sort was pretty good, nice and fairly fast. But none of them used this divide and conquer mentality. Okay? And when you're talking about sorting, and you're talking about most algorithms, if you can divide and conquer the algorithm, in other words, break it into pieces that are smaller and smaller and smaller, you will probably get better overall performance. So what we're going to do is this thing called merge sort. It is a divide and conquer sort, meaning that you can generally do it recursively, and also meaning that it's going to be pretty fast. Okay? Here's the bottom line about what we need to do with merge sort. Okay? Take two lists like this. Notice that L1 is in order already, and L2 is also in order. What you're trying to do is merging L1 and L2 produces the complete ordered string of or ordered list of both of these. It's actually pretty easy to do. Anybody have any idea how we would merge these two in a relatively straightforward? Yeah, Ethan. Compare the heads and put the smaller one right into the list. And then what? Keep doing it. So this could be one way to interpret that. Check 3 versus 1, put 1 in here. Check 5 versus 8, put 5 in here.
No, still the head.
Still the heads. Right, so you're saying remove this one? Good point. OK. You've got it, but instead of the head, let's move a pointer. I'll show you what I mean, like this. Here's how we're going to do it. So Ethan's right. You're going to check the 2 at the beginning, and you're going to put the one that's less in here. Then you're just going to move the pointer over in the next one. I mean, I erased this one, but it doesn't have to be gone, right? And then we check 8 versus 3. Well, 3 is less, so we're going to put 3 in here and move the pointer over here. And then 5 versus 8, and 5 goes in here. And then 8 versus 11, and 8 goes in here. And then 10 versus 11, and 10 goes in here. And then this one's done. And when one of them is done, then you copy the rest of the other one. And it actually works every time if they are already sorted. Very simple, easy to do loop, and you can just go right through them. OK? Right through. All right? So using that idea, let's create a bunch of lists like this out of some random data. OK? All right. Here's the full algorithm for how to do this. OK? First, you divide the unsorted list into n number of sublists that are each one element. One element in a list means it's already sorted. OK? I mean, that's kind of a dumb statement, I suppose, but it's true. If you've got a list of 1, it's sorted. Right? OK. So divide it into a bunch of one-element sorted lists, and then repeatedly merge those elements into the next level up, basically. So you're going to take 2, you're going to merge them into a list of 2, and then they'll be in order. And you're going to take the other 2 and merge them into a list of 2. Then you're going to take those groups of 2, merge them into a list of 4, which is in order. Okay? Repeatedly merge them until you get the new sublists, or until you get the final sorted list. Straightforward. Okay, let me show you how it's done. By the way, this is called a top-down merge sort. There's also a bottom-up merge sort, which we're not going to talk about. But if you want to, feel free to do that for your homework assignment if you want. OK? All right, here's how it works. Bunch of unsorted numbers up here in an array. OK? And by the way, one of the things about merge sort is that there is a way to do it in place. But it involves lots of shifting around of numbers. If you don't want to do all that shifting, don't do it in place. Just create a new list or new arrays each time. You do waste space that way. And that's kind of one of the issues. All right. So we go down here and we say, all right, so we're splitting this into 2. 4 in this list, 5 in the others, because sometimes there's an odd number. All right, split this one into two lists of 2, and this one into a 2 and a 3. All right, and then a 1 and 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 a 1, and then this 2 also becomes a 1 and a 1. Now we've got all our little our one element sorted arrays. Now we're just going to merge them. We're going to merge these 2 and these 2 and these 2, and then this one and then those 2, and we'll be good to go. Right? First we merge these 2. Then we merge all these guys into their respective ones. And notice these are all in order now in their respective arrays. And then we merge these two together, and then these 2 together. And then finally we merge these top ones together, and we're done. See how that works? Not too hard, and then this ends up as a completely sorted list. Yeah, Jason.
Instead of using like the log n of arrays, can you just
Yep.
bounce like in between 2 arrays?
Couldn't you just bounce between 2 arrays? I think you probably could. You would just need 1 array. Yeah, you could probably do it with just 1 array. It's a little, I suppose it's a little trickier if you're doing it recursively to know which one you're working on at each time. But you could probably work the logic out to do that. Yeah. Either way, you're going to need at least, and by the way, this one, so you have 9 here. You need 1 array of 9, and then this one you can reuse probably or you can probably reuse space to get the next one to the next one. It's not, you don't need an extra one each time. Yeah. Good question, or good point. Okay, anything else on merge sort? Here's the complexity of merge sort. So it can be computed in place, as we said, but if you don't, it does take more time if you do. If you don't do it in place, you end up using double the amount of storage, which can be bad. I mean, if you have only a certain amount of memory, you're not going to be able to sort big arrays using merge sort, because you need double the amount of memory. And you guys don't remember the time where memory actually meant anything, right? But if you do want to get into things like mobile type programming or embedded programming like Arduinos or Raspberry Pis or some other computers, you're going to have to eventually worry about the amount of RAM that you have. Like RAM is not, especially for these tiny little devices, it's not as much as you want. Okay, and your desktop or your laptop, sure, it's lots. But on a tiny little mobile device, it's not lots of memory. So considering these things is kind of important. OK, merge sort is very fast, though, especially if you're using the double space. How fast? Well, it's order n log n, which is the best you can do in general for selections or for comparison sorts, where you're comparing numbers against each other. It's the best you can do. Best case, order n log n. Worst case, n log n. Average case, n log n. Look, if you need a relatively fast, or if you need a fast sort, and you want it to be always n log n, use a merge sort. Okay, it's a pretty good sort to use, especially if memory doesn't matter. Okay. All right. All right. Let's look at the next type of sort. Okay. Next type of sort is a fun one. It's called quicksort. This is the one that most sorts use some variety of quicksort in order to do fast sorting. Okay? It's a very good algorithm. It also happens to be n log n on average. The only problem is it actually can be up to n squared time at the worst case. Okay? And you think, well, why don't we just use merge sort? Well, quicksort is generally faster than merge sort for a lot of sorting tasks. There are cases where it's not. But most of the time, it's very fast. Okay? There's some degenerate cases we'll talk about. Here's the idea with quicksort. First of all, it's another divide and conquer algorithm, which means it's going to be order n log n normally. Okay? Basic idea here is to divide the list into 2 smaller sublists. Okay? The low elements and the high elements. Okay? The low elements on one side, high elements on the other. Okay? And then what you do is once you've got the low elements on one side and the high elements on the other, you recursively sort those individual lists. So you sort the high ones, and then it's going to be higher on one side of that one, and medium high on the other side, and then lower on the other side on the other 2 lists. Okay? And you recursively do that until you've got a sorted list. Same idea in some sense as merge sort. Okay? All right? So here's what the actual algorithm is. All right. You pick what we call a pivot from the list. Okay, you pick one of the numbers in the list and you say, that's my pivot. That's the number I'm going to compare against. Then you reorder the list, okay, based on that pivot. And you say, the elements that are less than that pivot go on one side. The elements that are more than that pivot go on the other side. Okay? After that, we call that partitioning. After that, the pivot ends up in the right place. And now you've got two lists that are one's less than all the pivot, or less than the pivot, one's greater than the pivot. And then you can go ahead and recursively do the same steps to the smaller lists. Okay? If you end up with a list of 0 or 1 elements, well, they're sorted. Okay? That's how quicksort actually works. Kind of like with merge sort, there is what we call a naive algorithm where we create new lists for every subsort. Okay? That actually uses more extra memory, again, about n more memory, which we'd rather not do. We can do it in place. I'm going to show you both versions here, so you can see both versions of this. All right? All right, here's the naive one. Pick a pivot. We're just going to pick the first number there. Boom. And we're going to say that's our pivot. So in this case, 6 is our pivot. Right? And what we're going to do is we're going to take all the rest, and we're going to go through the rest of the list, and we're going to say, is it greater than 6 or less than 6? Or equal to 6. But we'll just, like lots of things in here, we'll just pick a case and say if it's less than or equal to 6, it's on one side, and if it's greater than 6, it's on the other. Okay? Or the other way around. Doesn't really matter. Okay? All right. So you've now got two lists. 5, 3, and 4 are less than 6. 9 and 12 are greater than 6. Okay? And I actually think yeah. So now we've got our pivot is 5. Okay? And 3 and 4 are less than 5. And over here, our pivot is 9, and 12 is greater than 9. Okay? And now we're going to put 5 there, and 9 there, and 6 there. And this one, I goofed on this one. The pivot should be 3, so it should be less than 3 or greater than 3. And so I guess 4 should be here. But either way, it's going to be same idea, though. And then you've got 3, and then 4, and then 5, and then 6, and then 9, and then 12. Okay, it's all based on picking a pivot and then getting all the rest of the numbers on either side of the pivot. Okay, and then look, it's sorted. You put them all back together, and they're sorted. Okay, very fast. Questions on that one? Yeah, Margaret.
So in the very bottom case, 3 versus 4.
Yeah, the pivot should have been 3, and so this should have been less than 3 and greater than 3, but yes.
Wait, so do you compare the pivot to itself?
You do not need to compare the pivot to itself, but you need to compare everything else to the pivot.
And then you put the pivot between.
And then you put the pivot between them. Yeah, in this case, there would only be, in this case, only 4. There's nothing else. So you put 4 there, and there would be no other. There's some good videos online, lots of good videos online about seeing this, people demonstrating it in various different ways. Okay? All right. So that's the way we do it with the kind of the naive create new arrays approach. There is, however, an in-place one. Now, this algorithm is a little bit tricky to understand. Well, it's not tricky to understand. You just kind of got to keep a couple things in your brain at once. What we're going to do is I wrote up the actual indexes here, because we're going to have a function. Okay, now if you create quicksort, you should create this function. If you do quicksort for your homework, this is the function you're going to want to do. Quicksort the array that you're passing in, and then the first element of the array and the last element of the array. The first index and the last index. In other words, 0 and 5. Get it? All right. Pick your pivot. And what we do is now we've got a pivot. We're going to have 2 more pointers. One's going to point to the beginning of the list. One's going to point to the end of the list. And we're going to move them towards each other, and you'll see what happens here. Because remember, we're trying to do this in place, just swapping things as we go. All right. We have a left pointer that points at 6. Actually, it probably could point at 5 and be just fine. But what it's going to do is the rightmost pointer is going to start out with the rightmost pointer. And it's going to start moving left until it hits a value that should be left of the pivot. So it happens to be right now on 4. Should 4 be left of 6? Yeah, because it's less than 6. Okay, 4 should be less than 6. Left goes to the right until the value should be to the right of the pivot. Okay, starts here. 6 should not be to the right of the pivot. 5, should 5 be to the right of the pivot? No. Should 9? Yes, okay, so watch. We're going to move left over to there. And all you're going to do now is swap the left and the right. Okay? So 9 and 4 are going to get swapped, like this. Okay? 9 and 4 get swapped, and then you repeat the process. You go back with the right until it hits something that should be less than 6. 9, you're going to go back, and it's going to be 3, which is less than 6, so you stop moving this one. And then you do this one until it gets to be something that that's greater than 6. Boop, right there. What do? Swap them. Swap 12 and 3. Okay? Swap 12 and 3, and now you've got that. And you repeat, which means you move right this way. And you keep repeating until they collide into each other, basically. Okay? Until they cross. So, boom. So you've moved right to here, and now left and right point to the same thing, and you go, OK, stop, swap the pivot with this one, and you're good to go. OK. Have we now come up with an array where we've got a pivot in the middle somewhere, and on the left is all the ones less than it, and on the right are all the ones greater than it? We do. OK. What do you do now? You recursively do this list and this list. I guess you would do, it doesn't really matter, you can do it either way, but this list and this list. How do you do that? You're going to call quicksort on it, like this. You're going to say quicksort from 0 to 3, 0, 1, 2, 3. And then you're going to go quicksort 4 and 5. That's breaking it up into this piece and this piece. Yeah, Jason.
Why do you need to include 6?
Yeah, you probably don't need to include 6. It might be a little faster if you don't. Yeah, if you just have to make sure that you know which one to. This one would be one less, 0 to 2. It probably doesn't matter. I think you can write it either way. You just have to check and make sure it works. You get the logic right. Yeah, Margaret.
Because you're swapping values, you do need some kind of temp.
Sure, you need some kind of temp to do it. Yeah. Okay. All right. So now we're going to recursively do this one. I won't go through the whole thing. Yeah, Yuval.
If for a function our arrays of private member variable function, include it in the parameters.
If it's not, yeah, if it's a private one, you don't need to include it. Like if it's already part of the function, you do not need to include it. Yeah, I was just if you passed in an array, you would do that. Good point. Yes.
How do you figure out what capacity started?
Good question. So you return. I think I glossed over this. You return the index of the pivot, and then you go from 0 to the pivot, and then from the pivot plus 1 to the end. Right? Okay. All right. So then we do the same thing. Right moves to the left. We'll do this one. Right moves to the left until it should be left of the pivot. 6, 4, 5, 3. It never actually is left from the pivot. It's just it actually ends up crossing. Well, then you swap the pivot with itself, basically, right? Then you're not going to actually do anything else. And then you're going to keep going, and you're going to keep doing it again. You're going to have the pivot for 0 to 0, and then 5 to there. This is probably one of the reasons is that it's hard to do. You have to figure out a case where you've got 0, 0. That might be one of them. But anyway, point is then you just do it again, and et cetera, et cetera. You keep doing it down. And then eventually you will end up with an in-place, quick-sorted array. Okay?
How do you determine when you end?
You end when you get a base case of either 0 or 1 elements to sort. For all of them, yeah. And then it will back up. Because it's recursive, all of them will eventually return, or return, I guess it would be return -1 or something. Whatever you say we want to return to say, oh, I'm done. That's it. Okay. All right. Good. Okay. So that is the quicksort algorithm. There's a couple things we have to talk about specifically about quicksort. So the idea of picking the pivot. So previously, I've always picked the pivot to be the first value here, right? That actually can lead to some problems. When this algorithm was designed, the guy who designed it said, just pick the first value, because it doesn't matter which one of the values you pick, just pick the first one. Problem is, well, can anyone think of the problem? If they were already ordered, right? Let's say they were already in order. Okay, they were already well, 3, 4, 5, 6. If you picked 3, then you would always end up with a 3 and like the rest of the array on the other side. So quicksort, picking the first element as the pivot, always degrades to an n squared sort if the list is already sorted, which you'd think is ridiculous, because if it's already sorted, you shouldn't be taking all this time to sort it, right? So that's not a very good way to pick your pivot. There are some other ideas. You can pick the pivot randomly, right? You just go through, you have some function which is random or what we call pseudo-random, so you just apply some function that kind of picks a value somewhere out of the array and say that's my pivot. And if you do that, even if it's already sorted, well, you will on average get a pretty decent pivot. So that's not a bad way of doing it. The other way of doing it is choosing the middle item. So you say, OK, look, it could already be sorted. I'm going to pick, boom, right the one in the middle. And it could be a poor pivot, but you never know, right? But it's better than most. There's often, more often than not, there's sorted lists already, as it turns out. You can pick the middle value. There are some caveats to that. You can't quite, like picking the middle by saying the left plus the right divided by 2. Sometimes that will overflow. Not the end of the world, but sometimes that happens. So you should probably, it's better off to do left plus right minus left divided by 2, which is just another way of saying the middle value. OK? All right, so that's the problem with that. Yeah, Lydia.
How does it overflow?
Good question. How does it overflow? If you do, so let's say you have two numbers. Let's say the maximum integers you can have are 2 billion, right? And if you had 1,900,000 and you added it to 1,900,000, you would overflow, right? In other words, you add those two numbers together and they're too big to fit in the space you have. You can't go above 2 billion, right? So if you tried to add them together, you get an overflow before you finish your calculation. So it's just kind of another little caveat about what computers do, right? It's somebody wanted to talk about the philosophical approach to computer science. Philosophically, it's you have to always think about how much the computer can actually do and the design underlying it. A lot of languages you don't think about that, but in things like C and C++, you have to think about the fact that you can't add giant numbers together, even if you're going to divide by 2. Because the first thing that happens is you try to add those numbers together, and if they don't fit in the spot you have for the numbers, they what we call overflow. Yeah.
So the problem with choosing the leftmost element every time is only problematic if your array is already sorted.
Or if it's almost sorted. I mean, if it's almost sorted, then the bottom values are generally going to be the lower values.
That's the only negative. So that, to avoid that negative, one way to choose something that's in the middle or
Choose randomly. Yes. Yep. Yep. OK. So that's good. Now, by the way, let me show you quicksort. I know I showed you this the other day, and I said, this is crazy looking. Well, it was. Let's see. Sorting algorithm animation. There we go. All right. Here it is again. Now, I showed you this one the other day. But let's look now that we understand a little bit more about what it does. Let's do this. So if it was random, this is going to be an in-place sort. So keep your eye out for both the left and the right pointer, or in this case, the top and the bottom, that are going to go towards each other. See how those are going towards each other? Right? So now it's just doing all the in-place quicksort. OK? All right, not bad. All right. Nearly sorted, it randomly picked a pivot, and so it does relatively well here. OK. And then reversed goes pretty fast. Take a look at this last one here. Few unique values. That means that there's some values that happen a lot, and like many of the values happen more often than, or often. OK? Now, watch what's happening here. Notice something about this. It's like super duper slow. This is one of the places where quicksort falls down, right? Trying to deal with a few unique cases. It actually turns out to almost be n squared behavior. All right, this, I mean, still going on here, right? And it's n squared behavior for the following reason. Okay. Let's pretend the whole list was all the same value. You're trying to sort a whole bunch of 4s, right? You're sorting a whole bunch of 4s, and as you're going along, you pick a pivot. Take a random pivot. That's fine. It's a 4. Well, all the items are going to end up on one side of the pivot, right? And then you've got your pivot, and you've got a list of 1 minus the pivot. And you do that one, and all the items are going to end up on the other side of the pivot. And you've only reduced your problem size by 1 instead of by half, right? So So that's the problem with picking with multiple, a small amount of the same values in quicksort. What do you do about it? Well, there's a couple different things you can do about it. There's another algorithm that says, fine, you want to deal with you've got a lot of the same values. Let's have a third case. Instead of just a left and a right, we'll have a case of equal to the pivot. All right? And anything that's equal to the pivot goes in that third part of the array. Okay, we're going to separate into 3 groups instead of 2. And then that means that equal values actually don't get into this situation where they're on one side or the other. They can get into that third place. So this one's called Quick 3. It's another type of algorithm that is available to you. Okay, and most quicksorts do that. Now, last comment about quicksort. I think I mentioned this before. Quicksort, well, first of all, quicksort is not that great on not that fast on small arrays, like by 5 to 10 numbers. Why? Because it's got to do all this recursion, and it's got to do all this partitioning and moving back and forth. It's just not that fast. So what normally happens is you implement quicksort, and then when your arrays are small, you just do a straight up insertion sort, which is fast on small arrays. This is one of those hybrid sort of situations. Okay? Questions on that, on quicksort? All right. Let's move on. Well, talk about complexity. Order n log n, worst case n squared, average n log n, space complexity. So if you do it naive way, you need at least n extra. Otherwise, you're going to have at least log n extra, and that's kind of a shady reason. But basically what's happening is even if it's in place, you still have to do the recursion, which takes up some extra space overall on the stack and so forth. I don't necessarily like that, that reasoning, but that's what they say. OK, last sort we're going to do. Okay? Completely different type of sort. This one's called radix sort. And it's completely different because it's not a comparison sort. In other words, it doesn't take 2 values and compare them to make a decision on where it goes. It's actually completely different. Okay? What it does is it uses these things called buckets. And the buckets are based on the value of the decimal place that you are at, if we're doing a decimal radix sort. Okay? What it does is it goes through the numbers. And at each pass, it says, what does your units place say? And then it puts it into a bucket based on that. Or what does your tens place or hundreds place say? It puts it into a bucket on like another pass. Okay? Watch how this works. Or I guess I'll talk a little bit more about the details in a sec. Yeah, most of this is in there. The buckets are individual arrays. And for decimal numbers, so you've got 9 digits, you're going to have 9 decimal numbers. 9 buckets. No, sorry, 10 buckets for decimal numbers, 0 through 9. Okay? Here's how it works. All right, here's a bunch of numbers. Now, I've written them out with all 3 digits, even though some numbers like 0, 3, 2 should only have 2 digits. They still have a tens place or a hundreds place. The hundreds place is just 0. Okay? So here's what you do. You take the numbers, and you go through the pass, and you check all the numbers. And you say, the first one is the units digit. In other words, the least, what we call the least significant digit. The one that matters least in this whole thing is the one that's in the ones place. Okay? And you check. Anytime in the ones place there's a 0, it goes in the 0 bucket. These numbers were specifically chosen because they don't have any numbers greater than 3. All right, I guess you could say this is base 3 radix sort, but the numbers could be base 10 because none of the numbers are greater than 3. OK, so anytime there's a 0 in the ones, you put it in the 1 bucket. Anytime, so 310, 130, 330, notice they're all zeros. And then the ones that have the units placed being a 1 in this bucket, 2 in this bucket, 3 in this bucket. Make sense? OK. Then you put them all back together, and you concatenate them again. You say this line, then this line, then this line, then this line. And they go back into the array. And then you do the same thing for the tens place. All right, so this is the ones place. You do the same thing for the tens place. You say, in the tens place, anything with 0, like 201, right, or 301, goes in the zeros one. And notice they're still in order in the ones place, 1, 1, 2, 2. But now they've got the zeros place in here. And you concatenate them together. And then you go ahead and do it for the, again, these are the ones that go in the 0 bucket. Then you do it for the hundreds place. Put them back together, and you do it for the hundreds place. Now everywhere where the hundreds place is a 0, like 002 goes here, 003 goes here, et cetera, et cetera, et cetera. Right? And then when you're done, you peel them all off, and they're in order. Kind of cool, huh? You never had to do one comparison, but you just threw them into buckets in the right order. And now they're actually in order. Kind of a cool idea altogether. Okay? In practice, these are normally done with queues. Now, I'm going to show you an animation in a second that actually, this Java applet, which shows you what I'm talking about. What it's doing is the numbers go in, and then when you're resorting them, in order to keep them in the right order from the previous sort, you kind of push them out in the same order you pull them in. Let me show you what I mean. Okay? All right. OK, the Java applet is giving me problems. Here we go. Run the animation. OK. Take a sec to go up. OK. So here's what we've got. We've got a whole bunch of numbers, and these are the actual buckets. And it's like modeling them like real buckets. But they're really queues. I mean, they look like stacks right now. But you'll see in a sec they actually go first in, first out. OK? You don't actually need the whole timer, the timer to be faster. OK, there we go. All right. So what I'm going to do, it's going to empty all the bins. OK, it's going to process all the ones that by the ones digit. So the next one will be 5, and then a 1, and then 4. This 8 is going to go in the 8 bucket down here, this one, right? Because the ones place is the 8. OK, just like what we just talked about. All right. Once it gets done doing that, it actually brings them all up here and then shoots them out in the same order they came in, but by the tens place. So now 9 is going to go over here, and 5 is going to go here, and 6 is going to go here, right? And so on and so forth. OK? See how that works? And then once it gets done with all these guys, once these guys go down here, it's going to move them up again and then spit them out in order by the hundreds place. Same idea. There's a link to this animation if you want on the website. Okay? And it's going to do the hundreds place. And I kind of wish there was one more setting on speed. It's just a little bit slow. But basically, it's going to do it with the hundreds place. Then it's going to do it with the thousands place, because these are 4-digit base 10 numbers. Okay? And once it's going to do, let's see that, and then the thousands place. And then at the end, it's got to spit it out one more time. Like I said, I wish it was just a little bit faster. But it's going to have to spit it out in order one more time in order to get the final ordering. Okay? You'll see in a sec. Sorry? You would not need any more buckets. You need the same amount of buckets. You just need to do it one more iteration through.
How do you know that? You have to figure out what's the most number of digits you have before you start.
Generally, you'll know that. Like if you're looking at integers, you'll know that you've got 32. You've got maximum of like 11 digits or 12 digits or something like that. You'll know that by the type of number that you're dealing with.
So
In general. Question.
when you say that, you mean you know that because you're running 32 bits packages, you would do it this many times?
Yes. Yeah, you'd know that the number of bits that you're in your numbers that you can handle are this many times. You don't have to, but or you could check and see which one's the highest number and go, OK, so it's like I only need to do it so many times. Yeah. Yeah. Alex.
Does it work equally as well if you started it with starting with 1,000?
Ah, that's like you're feeding right into my trap here. If, by the way, first of all, space complexity does take up a bunch of space. I'll get to your question in 1 minute. The complexity is tricky, because with comparison sorts, we're kind of comparing how many different comparisons it's done. This is a totally different methodology, so it's a little trickier to compare it. Really, the order is the number of digits times n, which is order n, right? Or order, basically a constant times n. If that's the case, you'd think, why don't I always do radix sort? Well, the answer is it's because it's not quite so simple. When you're trying to figure out if the tens or hundreds place in a number is a certain value, that actually takes a fair amount of time. So it's not just about the fact that it's the overall order is this. It takes more time to do those kind of calculations. So that's the reason we don't always use radix sort. But to answer your question, Alan, if you do it by the most significant bit, you end up ordering it slightly differently. You end up ordering it by lexicographic order, which you wouldn't think is much different. Except what that means is things like words end up in order, right? B, D, E, cat, bat, car sorts B, bat, car, cat, D, E, right? But that's kind of backwards from like car and cat. Well, actually, this one's actually, this is not, with letters it makes sense in alphabetical order, right? And in fact, if you think about it, if these were numbers, wouldn't B be like somehow like less or greater than bat? No, it would be less than bat. No, you're right. It would be less than bat. For letters, it works this way. For numbers, though, it ends up sorting them like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sorts like this. 1, then 10, then 2, 3, 4, 5, 6, 7, 8, 9. So it ends up slightly different for if you do it by most significant bit. And it ends up in what we call lexicographic order. And what it's kind of like is if you padded the keys, so like 1 wasn't just 0, 1, it was like 1 something, right? It's actually less than 0 in this case. I mean, it's padded, though, in some fashion or another. OK, so yeah, so absolutely the order matters, the way you do it. Yeah, Bob.
For radix sort, why wouldn't the initial sort be 10, then 1, 2, 3, 4, 5, 6, 7, 8, 9? Because the least significant digit of 10 is 0.
Well, because this is padding as if it's like some value less than 0. Because it's hard to explain. It's kind of reversed in the sense of the way it pops out of when you're doing it by most significant bit. Try it, like if you want, code this up and try a most significant bit first and see what happens with walk through each one and see what happens. Yeah, Margaret.
Does it matter if the buckets are treated like queues and not stacks?
It matters that the buckets are treated. You could have the buckets being another array, like I did in kind of the other example where I had them like that, where you put them into individual arrays and you just have to know how to feed them back so they're in the right order. That's the only mad thing. Each little individual stack would be reversed if you did it with a stack, or each little bucket would be reversed. Okay? All right. A bunch of sorting references, some other videos here, a couple really good videos, so check them out. And any other questions on sorting? All right, today's lab is on tries. Did you guys end up finishing it? Did you get? Yeah, weird bug. OK. It's on tries, which is kind of from, you got it done? Awesome, good. It's graphical a little bit. You can actually, it's web-based. You'll see. All right. Talk to you guys. See you guys in lab or on Wednesday.